Welcome, everyone, to this session on emerging pollutants and wastewater. My name is Mary Trudeau. I'm an engineer based in Canada, and I'm also a project officer with the I-WRA, and I'll be moderating this session. So this is the first of two sessions looking at wastewater. The second one will be tomorrow morning at 9 a.m. Central Time. And I'd like to also introduce my co-moderator, Dr. Suryakanta Acharya. So Dr. Acharya is the founder of PW Clinic, a not-for-profit organization working on health and climate change, and he's also active with the IWRA. I'd also like to acknowledge our rapporteur, Nusrat Balush, who is in the audience. You won't see, but who's vigorously taking notes for us. So Dr. Acharya will be monitoring questions from the audience, and we'll have 10 minutes to answer your questions after we've heard from all of the speakers. So during this session, we'll have 7 speakers, 4 10-minute presentations, and 3 what we're calling lightning round presentations of 5 minutes each. So I'd like to invite you to submit your questions in English using the Q&A button. You can find that at the bottom of your screen. And please, if you could indicate the person to whom you're directing your question, that will assist us. And you'll only see your question responded to once it's either answered verbally or in writing, and then they'll be displayed for everyone to see. So we have a very large audience, and if we don't have time to answer all of the questions we receive within the next 75 minutes, we will aim to collect written responses from the presenters, and we'll place those on the conference website following the event. So also note that the chat box is disabled during this session, but we ask you to keep your eye out there for some useful messages that may be shared by the organizers. So there's also an option for you to switch on the automatic subtitles at the bottom of your screen if you're having difficulty hearing. Sometimes it helps if English isn't your first language as well, just to see it written. And just a reminder to all of our speakers that the session is being recorded. So with that, I would like to just get right into it. And it's my pleasure to introduce Dr. Cristina Valhondo. So Dr. Valhondo is a postdoctoral PhD researcher at the Institute of Environmental Assessment and Water Research at the Spanish National Research Council. So we just need a moment to bring up Cristina's slides.
Thank you, Marie. So good afternoon, everyone. I'm going to present the experiment that we make to evaluate the capacity of some materials with the idea to include them in a reactive barrier to increase the efficiency of soil aquifer treatment for water reuse. Next, please. Next, please. Okay, the demand of water is very related with the population growth and is expected to keep increasing. And one option to meet this demand is by exploiting groundwater, but this causes some detrimental effects as decreased groundwater levels and give poor quality of the rainwater dependent ecosystem and more expensive for the groundwater extraction. So given the framework, this framework, water reuse is a must. We can no longer afford not to reuse the water. And one option to do this is soil aquifer treatment, which is a special case of managed aquifer recharge that consists in induced infiltration of effluent of the secondary treatment of a wastewater treatment plant through the bottom zone and to reach the aquifer. Doing this, we increase groundwater, recharge water quality, and we also increase the groundwater resources. And besides, we reduce the direct discharge of this secondary treatment effluent into the aquatic environment. Next, please. Next, please. But we have to be careful because, no, the one before. We have to be careful because the secondary treatment effluents are characterized for containing a number of contaminants, such as trace organic contaminants that are not completely removed in wastewater treatment plants, mainly because these plants are not designed to remove these contaminants, virus and bacteria that even if they are efficiently removed, they are not completely removed. And besides, we know now that a wastewater treatment plant represent a hotspot for antibiotic resistance. That is going to be one of the major issues in the coming years. And also micro and nanoplastic that are highly persistent, and they include another problem that is that they can facilitate the transport of other contaminants. So it's very important that we know the fate and behavior and the processes that control the behavior of these contaminants during soil aquifer treatment in order to avoid groundwater contamination. Next, please. So the main two processes involved in the transport of these contaminants are sorption and biodegradation. And both processes are dependent on a number of parameters, including the physicochemical properties of the molecules, the surfaces, and also the redox state of the environment that controls the microbial community and the pathways, the metabolic pathways that they apply and they degrade the emerging contaminant. Next, please. So knowing the parameters controlling these processes, we can manipulate the system to increase the efficiency of these systems. One approach is, for example, to install reactive barriers in the infiltration area of this system. And this reactive barrier can apport new sorption site that will increase sorption and also release dissolved organic carbon to recharge water. So we will develop a broad range of redox condition and we will increase biodegradation. And these reactive barriers have been already tested in field scales and they are very they show very promising results. Here you can see a scheme of a soil aquifer treatment working in a conventional way and the soil aquifer treatment operating with a reactive barrier. And you can see how the redox environment are increased in the second case. Next, please. So the objective was to study the capacity of several materials in order to improve the sorption of emerging contaminants. And we do so through batch experiment. Next, please. First, we select the 5 materials and we compare their sorption capacity to sand. That is the material that we normally find in the infiltration area of SAT systems. The materials we select are based in their sorption capacity, like clay or zeolite, or because they are able to release a great amount of dissolved organic carbon into the recharged water. In this case, we select compost, wood chip, biochar, clay, and zeolite, and we measure the physicochemical parameters in the laboratory. And we have a big, a great broad values of these parameters. Next, please. Then we select a number of emerging contaminants with different physicochemical properties also. And next, please. In the case of ofloxacin, for example, it presents 2 pKa, so it changes from cationic to neutral to anionic. And the capacity or the tendency to be solved into organic phases is represented by the orange line and is pH dependent. Next, please. The methodology consists in putting together a volume of water speaked with known concentration of these molecules and a volume of crushed material for 60 minutes. So the time is not enough to have biodegradation. And we also perform batch experiment without material to see if we have losses of the molecules due to other processes other than absorption. Afterward, we separate the phases, we analyze the concentration of the molecules in the supernatant, and we are able to define the source, the amount of molecules sorbed in the different material. Next, please. Clay and zeolite display very similar behavior, and we can see that they increase the sorption of the cationic molecules, that are the green ones, compared to sand, and also the neutral. But the anionic molecules are very similar in the three. The behavior is very similar in the three components. Next, please. While the materials displaying high organic carbon content increase drastically the sorption of all molecules. Next, please. But especially what we find is that cationic molecules are very easily sorbed. Neutral are highly sorbed in all the materials displaying high organic carbon content, while the anionic molecules are those presenting the lowest sorption properties. And that indicates us that these kind of molecules are those that are going to represent a higher risk because they are more mobile and they will reach more easily the aquifer. So it's these molecules in which we have to put our attention. Next, please. So to summarize, we studied the sorption capacity of several suitable materials and compare with sand. And the physicochemical properties of the molecules and the material play a role in the sorption contaminant, especially the molecules ionization and the organic carbon content of the material. The molecule ionization, we can also control in a way by adding some materials that give a lower or higher pH. So we can have some capacity to manage the system, adding some materials. And finally, the optimal situation will be to have a mixture of different materials to increase the number of molecules that can be sorbed into this material. Next, please. And finally, I want to thank you all for attending the talk, and also the team who I performed the experiment with in Montpellier. Thank you.
Thank you very much, Cristina, for that presentation. Yeah, the importance of managed aquifer recharge, water reuse, but water reuse with the quality that won't have harm is so important. So that was super interesting. Thank you. So our next presentation is Ahmed Rezk, who is an engineer with the BENA Foundation, which is a youth-led not-for-profit organization to build capacities of youth for sustainable development projects in the MENA region. So welcome, Ahmed.
Hello, good evening, everyone. Today I will be presenting our presentation about the project we are working on, which is Safe Agro MENA, a project that consists of a consortium from 4 countries, including the Netherlands, Egypt, Jordan, and Iraq. And in this presentation, my colleagues who participated in it as well were Dr. Muhammad Tawfiq, and engineer Ashrakat Osama, and Hadir Hosni, Asma Yusuf, and Professor Peter van der Steen. Could you please go to the next slide, please? So in this presentation, I will mainly discuss the 3 main themes. First is the emerging contaminants as an environmental hazard in Egypt, and the impacts of these contaminants, especially in Fayoum governorate, the place we are doing our project. And finally, an introduction to our project and how it's taking a more integrated approach to mitigating the impacts of emerging contaminants. The next slide, please. Okay, so first of all, we started by defining the emerging contaminants as the contaminants that are usually available in the environment. However, they are not commonly monitored, and they have adverse ecological impacts, ecological and human health effects. The next slide. And mainly these contaminants have three main sources. Either they are organic compounds such as pharmaceuticals and industrial chemicals, or inorganic compounds such as heavy metals, or particles such as micro or nanoplastics. The next slide, please. And back in 2013, a paper in the Egyptian Journal of Occupational Medicine found that emerging contaminants are existing in different wastewater sources, such as domestic activities and agricultural activities and industrial activities. The next slide, please. Therefore, in order for us to define the emerging contaminants at the beginning of our project, we resorted to two main sources. First is the detection of the literature on the detection of emerging contaminants in Egypt, and also on the most prescribed medicines in Egypt and their consumption. And out of these lists, we check the human and veterinary use of the pollutants and the mode of action of each contaminant and the environmental impact of each contaminant. The next slide, please. And that was the list that we found out. And as you can see, the list is dominated by antibiotics that are usually overprescribed in Egypt. The next slide, please. And we are now we are working in Fayoum area, which is like a microcosm of Egypt, because it's very similar to Egypt in terms of the water comes from one source and ends up in a large water body, which is Karun Lake. Please, the next slide. And the impacts of these contaminants in Egypt, in Fayoum, has like three main lines. First is the contamination in the Karun Lake, and also then the contamination in the agriculture product, which reduces the value of the product and reduces the productivity of the land. The next slide, please. So the increase in agri and contamination in Karun Lake affects the fishing, the commercial fishery in the Karun Lake, and also given that the agriculture sector employs a large section of the Egyptian population, especially in Upper Egypt, this has an adverse economic impact. The next slide, please.
Excuse me, Ahmed, can I ask you
yeah.
to summarize your bottom line, please, on your presentation?
Yes, sure. Okay, so I say like very rapidly that given that the different adverse impacts of the emerging contaminants in on the environment, and also the different sources of these contaminants, as we could see in like the following slides, there is a need, I think if we could go to the last slide, please, to use. Yeah, the next one. Yes, so mainly like the one before it. Yeah, this one. So mainly the integrated approach we are taking is by starting to identify the socioeconomic aspects and the environmental aspects as well, leading to the emergence of these contaminants in the environment. And then we're using a participatory approach, starting to develop an agro-ecological interventions with the help of the different partners in order to improve the quality of the water used in Egypt, in order to enhance the agricultural product and the food security in terms of the economic impact and the agricultural productivity. Thank you.
Thank you very much. Yeah, that the interdisciplinary nature of the issues is so important to acknowledge. Thank you for that. So our next presenter is Edith Nwakaego Okey. Edith works with the National Water Resources Institute in Nigeria. She's the eco-hydrology officer at UNESCO's Regional Center for Integrated River Basin Management, and she's also a PhD student in environment, sanitation, and waste management. So welcome, Edith.
Good afternoon, everyone. My name is Edith Nwakaego Okey. I will be presenting on the removal of pharmaceutical pollutants using ceramic membrane filter. Next slide, please. Emerging contaminants. Next slide, please. Emerging contaminants are classified as emerging contaminants. No, please. Next slide. The previous ones. Emerging contaminants are various chemical compounds that are not commonly regulated in the environment, but have the potential to enter the environment and cause a negative effect on ecosystem and human health. So emerging contaminants are classified as pharmaceuticals, hormones and steroids, personal care products, surfactants, agrochemicals, microplastics, among others. There has been a worldwide concern about the inability of the traditional wastewater treatment plants to completely eliminate pharmaceutical contaminants from wastewater. And the reason is because they are not designed to remove these contaminants from wastewater. So to address this inadequacy in conventional wastewater treatment system, a lot of advanced treatment system has been developed and evaluated. Such treatment systems include ozone or advanced oxidation processes, activated carbon filtration, membrane bioreactors, among others. So even though using this treatment system, high removal efficiencies were achieved, but they are expensive to operate and construct. So it has become very important for us to develop a treatment system that can effectively remove these contaminants from wastewater using easily accessible and affordable raw materials from the local areas. Next slide, please. Clay can be molded into various shapes, which they retain when they dry. So naturally occurring clays are widely used for contaminant remediation due to their easy availability, high absorption capacity, high porosity, high cation exchange capacity, and high surface area. Worldwide, clay has been useful by man from time immemorial for both industrial and domestic application. Today, clay is still very useful in ceramic industry for processing several forms of ceramic materials. However, the particular application of clay depends on its mineralogy, physical and chemical properties. Over the years, ceramic filters have been applied as an alternative treatment system for treating wastewater, stormwater, and drinking water. So ceramic filter achieve these removal processes through size exclusion, membrane absorption, charge repulsion, sedimentation, biodegradation, among others. Next slide, please. Next slide. So the aim and specific objectives of the study. The aims and specific objectives of the study include the main aim of the study is to investigate the efficiency of the ceramic membrane filter for removal of pharmaceutical contaminants from wastewater through filtration experiments. 2 is to determine the effect of operating parameters such as flow rate, pH, sludge retention time on the pharmaceutical removal efficiency. 3 is to determine the effect of plugging on the ceramic membrane filter for 4 months continuous operation. Next slide, please. Next slide. Materials and methods. So ibuprofen, diclofenac, paracetamol, morphine, and tramadol of purity greater than 99% were used in this study. So Oasis HLB SPE cartridges were used for sample extraction. Reagents such as methanol, acetic acid, acetonitrile, TFA were used for for sample preparation and HPLC analysis. So for the fabrication of the filter, 2 different types of clay were used, such as Nwakaego clay, M.Sc clay, and then this cassava starch was used as a pore formers. Next slide, please. Next slide. Now, this particular slide shows the operating parameters of the HPLC that was used for the analysis of the selected compounds. So over here, you can see the chromatograms of the HPLC analysis for the 6 selected compounds. Then the analysis of these compounds were achieved by their comparison with the retention times in conjunction with the PDA, which is photodiode array, the detector. Next slide, please. Now, over here is the slide showing the different processes that took place during the filter fabrication. Next slide, please. Now, this is the setup for the ceramic filter experiment. So you can see that the filter was treated, the wastewater treated at the flow rate of 50, and then the one treated at 150 and 300. So the one treated at 50 is more clear and more clean than the one that treated at 150 ml per hour and 300 ml per hour. So this slide also shows the conditioning step of the SP cartridges and then the extraction processes that took place. So after the extraction processes, the samples, the analytes were eluted into a chromatographic vials, and they are ready for HPLC analysis. So after the HPLC analysis, the equation displayed here was used to calculate the removal efficiency. Next slide, please. Then results and discussion. Then after the application of the ceramic membrane filter for the pharmaceutical removal, we can see that the paracetamol, codeine, diclofenac, and ibuprofen were removed from 70 to 100%. These compounds are classified as basic pharmaceuticals, while for the diclofenac and ibuprofen, they had a very little removal efficiency from 16% to 19%. These compounds are classified as acidic pharmaceuticals. It shows that the ceramic membrane filter under normal wastewater conditions treats basic pharmaceuticals more than the acidic pharmaceuticals. Next slide, please. Next slide. Now, the effect of flow rates on the pharmaceutical removal. So we can see that as the flow rates increases, because the removal efficiency was tested for 5 different filters, such as 10, 50 ml, 50, 150, and 300 ml per hour, in order to select the best filter that can treat these pharmaceutical contaminants. So looking at the graph, it indicated that as the flow rate increases, there is decrease in removal efficiency. The reason is because as the water flows at a very high, flow rate, they have a less contact with the contaminant, has a less contact with the filter element, and that will also reduce filtration, that will reduce the rate of filtration, that will reduce biodegradation, that will reduce sedimentation, and that will also reduce absorption, leading to lower removal rate. So as the flow rate decreases, we have a higher removal efficiency. Next slide, please. Now, effect of pH on the removal, on the pharmaceutical removal efficiency. So we can see that using altering the pH, such as at different values such as 7, 4.5, and 9, we can see that the basic pharmaceuticals such as codeine, morphine, paracetamol, and diclofenac were removed from 83 to 100, while there was little removal, where there was little removal for the acidic pharmaceuticals such as diclofenac and ibuprofen at 7 and 9, and there was negative removal at the pH of 4.5, and that shows that the pH alteration does not have effect on the removal of the acidic pharmaceuticals. Next slide, please. The effect of sludge retention time on the pharmaceutical removal. So, because the removal of diclofenac and ibuprofen are very, very desirable to us because of from the scientific literature, it has been indicated that these compounds have a very harmful effects on the environment. So it becomes very necessary for us to look for a means of removing these contaminants, and that makes us to increase the treatments to apply sludge retention time and see if these contaminants will be removed. So we can see that from day 7 to 14, as for the basic pharmaceuticals, we can see that the removal efficiency ranges from 81 to 100. But for the acidic pharmaceuticals such as diclofenac and ibuprofen, there was a little improvement in the removal efficiency. So it shows that these times are not enough for their degradation, complete degradation. So extending the sludge retention time to 21 and 28 days, we can see that a high removal efficiency were achieved for these particular contaminants. Next slide, please. Now, looking at the effect of clogging on the ceramic membrane filters, we can see that the flux efficiency continues to decrease as the treatment period increases. And that is as a result of clogging, pore clogging, because from pore clogging, from the debts, from the wastewater. So at week 8, when it was washed, we can see that the decrease in the flux efficiency. So immediately after washing, we can see that the flux efficiency continued to increase until week 13 to 16, when it started to decrease again. And that shows that clogging is a major problem when using ceramic membrane filter. And it also shows that cleaning can be incorporated into the maintenance procedure of the ceramic membrane filter, and that can also improve the performance of ceramic membrane filter. Next slide, please.
Can I ask you? Oh, thank you.
Conclusion. Conclusion. The present study indicated that ceramic membrane filter experiments operated at a smaller flow rate combined with increased retention time achieved the best performance among the suited compounds. Now, considering the high removal rate of other pharmaceutical compounds under normal wastewater condition, the ceramic membrane filter can be considered as an efficient and economical treatment method and could be applied in several related industries. So the inability of the developed ceramic membrane filter to remove diclofenac and ibuprofen under normal wastewater conditions makes it easier for future researchers in the modification of the ceramic membrane filter with the objective of removing diclofenac and ibuprofen to an acceptable level. Thanks for listening.
Thank you very much, Edith, for that. It's encouraging, the results for a material that's as accessible as ceramic. Unfortunate about the ibuprofen. So we'll move on to Simeo Urpia, who is in the Chemical Engineering Department at the Federal University of Bahia in Brazil. So over to you, Simeo.
Mary, can you hear me?
Yes, go ahead. Thanks.
Okay. So good afternoon, everyone. My name is Simeo Urpia, and I'm going to talk a little bit about the data science applied to the emerging pollutants in the sanitation sector. And my work is an investigation in open databases. Can you move to the next slide? So the main goal of my research was to perform an analysis through investigation of the open databases on emerging pharmaceutical pollutants in wastewater, in the Brazil and in the world wastewater. Next slide, please. It's already known that emerging pollutants can cause adverse effects to the environment and human health, and these effects are often still unknown. It's already known. Furthermore, monitoring these emerging pollutants wastewater in treatment plants, it's often a difficult and highly complex task. We have to make multiple collections, and this analysis and the equipment generates costs continuously and that presents detection limitations. Next slide. So because of that, the data science emerged as a tool to solve these problems and to monitoring the wastewater without the need of the collecting methods. My study was divided in 2 steps. The first one was to make a database with open data extracted from other studies about the behavior of emerging pollutants in urban wastewater before and after real wastewater treatment plants, with the goal to summarize and help the search for this info in future works. And the second step was to make an exploratory analysis using the data tool R in another database, so we can cross the data from the other studies, the open data, with the data from this bank called Sales Anvisa that summarize all the pharmaceutical sales information in Brazil. Next slide, please. As main results of the study, we created a lot of graphs and tables that summarizes the info of the distribution of these pharmaceutical compounds in the wastewater and the sales. This one, for example, shows the distribution of the age with and without the outliers of the bank. So we have to treat this data bank to obtain the real trustable data. We can observe, for example, that we have customers in the first data bank that have more than 5,000 years old, and this is not a real thing. And we had to filter this bank to have only data about real people that have they have real ages. You can go to the next one. We've seen already that the most sale compound in Brazil was the amoxicillin hydrated one. In this graph, you can see that. And when we compare this data with the other studies data, we see that this may not be a real data. This data bank can have some problems in the collecting of the data, as we've seen in the other graph too. And it may not represent the real statistical data from Brazil. When we cross this data, for example, with the other studies, we see that paracetamol, diclofenac, clonazepam, for example, are pollutants that are much more common in the wastewater plants than the amoxicillin. And in this bank, we see that this is one of the most sales one. Can you move to the next one? We can see in this data bank as well the distribution in the cities of Brazil, the sales distribution in the cities of Brazil. And this helps to compare with the plants that are in the cities. So we can cross the data from the sales with the data of the exact city that this wastewater is being collected. And this helps to take more solid conclusions. The understanding of this data can help to solving complex environmental tasks and problems, not only being relevant as basis for further discussions on the subject, but also as a reference for defining public and private projects for monitoring and treating this class of emerging pollutants. Thank you for your attention.
Thank you very much for your presentation. Yeah, the problems with cleaning data sets. I think many people in the audience can probably relate to that, 5,000-year-old person who isn't there. Our next presenter is Wandimu Kebede, who's a PhD candidate at the Africa Center for Excellence for Water Management in Addis Ababa in Ethiopia, where he's researching removal of emerging contaminants from water using biomass-based observance. So welcome, over to you. Go ahead.
Thank you, Murray. And I would also like to thank UNESCO-IWRA committee for providing this opportunity. And I'm very grateful to all the conference organization team. And thank you all for joining this presentation. Our work is on high surface area chemically activated carbon derived from bamboo sawdust for the remarkable removal of paracetamol from water, sorption kinetics, isotherm thermodynamics, and regeneration studies. Next slide. Next. Yeah, rapid population growth and economic growth has resulted in the usage of various kinds of drugs and various kinds of pharmaceuticals, and which eventually come into the water bodies, and now it becomes current environmental burden. Next slide. This problem is obviously the result of anthropogenic activities, and which is severe in urban areas because of intense human activities in urban areas, like industrial activities, hospitals, and also other intense human activities in urban areas, which result in the release of these contaminants, especially emerging contaminants. These contaminants eventually reach the wastewater treatment plant, the conventional wastewater treatment plants, which in most cases is unable or inefficient at removing these contaminants of emerging concern. And these contaminants have been currently detected in surface water, groundwater, and even in drinking water at concentration ranging from nanogram to micrograms. And now it becomes a threat to human beings. Next slide. As a result, various technological options have been implemented so far, like advanced oxidation process such as ozonation, electrochemical oxidation, and adsorption process, membrane technologies, but still there is issues associated like cost, safety, and operational difficulty. These membrane technologies, in most cases, they are very costly, and operational difficulty is also there. So there is still the research intervention is still necessary to come up with low-cost, safe, and sustainable technological options. In this regard, adsorption seems to be very interesting because of its low cost. We can prepare adsorbents from low-cost materials and even from waste materials. Next slide. So in our work, we prepared an adsorbent from bamboo sawdust, which is a waste material, and activated chemically using potassium hydroxide and ferric chloride. And under heat, we chemically treated, and chemically treated bamboo sawdust was ground and carbonated at 700 degrees Celsius, and then used as an adsorbent in the subsequent adsorption process. Next slide. Yeah, here comes the result section, and here I'm going to present it very briefly. Here, the result section contains two results. The first one is absorption experimental studies result, and the second one is the material characterization result on the right part of the slide. So as you can see here, before activation, the bamboo sawdust carbon has 565 meters square per gram specific surface area. But while after activation, the surface area increased to 1,158, a significant increment. And the figure itself shows the same image of the material before chemical activation and after chemical activation. After chemical activation, as you can see here, various porous structures have been developed, which was very important in removing the contaminant, in this case, paracetamol in our case. And the FTR result also showed incorporation of various important functional groups which were involved in the removal of the targeted pharmaceutical, that is paracetamol in this case. When we come to the adsorption result study, the material that we prepared here from bamboo sawdust achieved or resulted in the removal of 99.6% of paracetamol, which means almost complete removal. And this high removal is associated with the high surface area of the material and some important functional groups incorporated during chemical activation. The absorption process was characterized by pseudo second order kinetic model, and Langmuir isotherm gave best fit to the absorption data. And thermodynamically, the process was spontaneous and exothermic in nature. And the absorbent material was tested to see the regenerability, and some interesting results have been obtained. And lastly, the absorbent was also checked on the real environmental samples and resulted in good results. And optimum conditions, in this case, we obtained this pH of 8, contact time 90 minutes, and adsorbent dose of 0.5 gram per liter, and paracetamol initial concentration of 20 milligram per liter. Next slide, please. So with this, now we have come to an end of this presentation. The adsorbent we prepared, the chemically activated bamboo sawdust adsorbent, is an efficient, resulting in almost complete removal, reusable from the regeneration studies, and low-cost adsorbent that we prepared from waste material. So this is a promising adsorbent, but this adsorbent need to be tested on multiple contaminant removal, like other contaminants, other emerging contaminants. We just only checked on paracetamol. So, and another thing is coupling adsorption with other technologies such as AOPs, advanced oxidation processes, has greater benefits because of the synergy, because each technology has its own advantage and disadvantage. So we intend to further test this adsorbent, this work, coupling with advanced oxidation process like ozonation, so that we can have some synergistic effect in removal of emerging contaminants, like multiple emerging pollutants at a time. So next slide, please. So these were some of the references we used during this work. And with this, we have come to an end of this presentation. Next.
Great.
Yeah, thank you very much.
Yeah.
And if you have questions, and just welcome.
Yeah, we'll get to questions at the conclusion. So very encouraging results from, again, a very accessible material. Super exciting. Thank you. So our next presenter is Kenny Dick, who is with the UNICEF University in Botswana. So if we have those presentation slides, I will hand it over to you, Kenny. Welcome.
Thank you, Mary, and thank you, UNESCO-IWRA, for the opportunity to also present at this conference. I will be giving you the highlights on my study that I'm doing with the UNICEF University, which is online. I reside here in Botswana, and my name is Kenny Dick, as I've already been introduced. The purpose of my study was basically to prevent pollution at its source. As you can see that the title is Sustainable Development, a strategic approach for sustainable business practices in trade effluent generating industries and in Francistown region in Botswana. Next slide. The study was based on the theory of sustainable development that emerged for the first time in 1972. And the theory has been evolving since, and it is currently being guided by the SD Agenda 2030. Next slide. The 2030 agenda is streamlined by the 17 Universal Sustainable Development Goals, which are intended to protect the environment, to ensure prosperity for all, as well as ensuring the social justice. And because this is a global commitment, Africa as a continent has also developed its Agenda 2063, which is also in line with the Sustainable Development Goals. And Botswana as a nation is also aligning their strategies and their national priorities, as well as the Vision 2036 is aligned with the Sustainable Development Goals. Next slide. Now, the study was based in Botswana, in Southern Africa, and in the city of Francistown and the neighboring village, Tonota. And the focus was actually on the trade effluent generating industries in that area. Next slide. Now, The motivation for this study was the pollution that is caused by the wastewater generating facilities. Historically, or the monitoring results over the years were indicating that the wastewater discharge facilities in the country, they are not in compliance with the wastewater discharge standard, BOS 93, 2012. And the major contributors to the pollution is the trade effluent generating industries. And this study was actually trying to find a solution that can help these industries to curb the pollution at source. Next slide. This was a qualitative case study where data was collected through the semi-structured interviews, as well as reviewing the documents that were collected from the industry. These were the annual reports, as well as the policy documents that were collected from the public domain and also from the government offices. And data was analyzed through data coding and then grouped into categories, and then themes and assertions were developed in order to answer the research questions. Next slide. Now, the results of the study, as I've already indicated, that the data was collected in the form of words, and these words were actually categorized or grouped accordingly to answer the research questions. And 6 themes were developed from the results of the study. Next slide is the last slide. Now, the recommendations that were given to the industry is that the industry has to uptake or to adopt the SD principles in their strategic framework in order to be able to curb the pollution at source, because we've already realized that it is difficult for the wastewater treatment facilities to treat industrial effluent because of its high strength or the composition of chemicals that it has. Thank you, ladies and gentlemen. Next slide.
Thank you very much,
ladies and gentlemen.
Thank you for your presentation. It's hopefully going to be able to work with the industry to improve that compliance rate. So our next presentation is Elena Emili Lucetti, who is a PhD student in theoretical chemistry, working with simulations of materials that can promote hydrogen peroxide electrogeneration for water treatment. And she's part of a collaborative multidisciplinary group based in Brazil carrying out this research on wastewater processes. So welcome, Lena.
Hello, everyone. I would like to say that I am very, very happy and grateful for the opportunity to be here, talking a little bit of our research for you in this amazing event. And I'm going to present a brief summary of our ongoing research, as well as talk a little bit about our last development materials, which are niobium-based for emergent pollutants removal from wastewater. So here on slide 2, we can see that the water contamination by emergent pollutants is a multifaceted and very complex issue, because the compounds can come from multiple origins and sources. They can come from the agribusiness, the industry, even from the medicine the population consumes. So they have a wide variety of chemical structures, and to top it all, new emergent pollutants are still being identified and discovered every day. So this is a very hard problem to address. And on the following slides, I have some quotes from the State of the World Drinking Water latest report by World Health Organization. And they say that despite all the progress we've made, still 2 billion people did not have access to safely managed drinking water in 2020. This is a huge part of our population. Moving on, they say that the science is still not clear on concentrations at which these contaminants can pose a risk, and also which are those contaminants. And finally, they recommend that the government and stakeholders, they should encourage and fund research in water sector, work with academic institutions, and disseminate these results to inform decision making. So in this context, we are an academic research group, and we are focused on emergent pollutants degradation with electron phantom processes, as we can see here in the slide 6. So electron phantom processes, for those who are not very familiar with it, they can be promoted by a light source, and it can be simulated or even natural sunlight. In these processes, we have an electrochemical cell where gaseous oxygen can be converted by the action of a catalyst to hydrogen peroxide. And hydrogen peroxide is already a very reactive molecule, but it can undergo phantom reaction and be converted to hydroxyl radical, which is an even more reactive species. And what those have in common is that they can react in a non-selective way with organic molecules, and these account for the structures of the vast majority of the emergent pollutants. So they can react with them in a non-selective way and break them down all the way to CO2, water, and inorganic ions. So this is a very interesting process when we were talking about a general solution to address the emergent pollutants contamination in water. So let's focus on our attention now on the oxygen reduction reaction here on slide 7. In this reaction, we have gaseous oxygen being converted to hydrogen peroxide by an action of a catalyst. The catalyst is the surface where the oxygen will bond, so the reaction can follow. So our group, our focus is to develop advanced nanomaterials for these applications. We have very interesting and cool materials. For example, this one in slide 8, which is manganese dioxide nanoflowers that were used to degrade azo dye. We also have cerium nanorods here in slide 9 that were used to degrade paracetamol. So we manufacture these interesting materials for this application. Let's go to slide 10, please. And now we have this, I'm presenting to you our latest material. So we work, as you've seen a little bit, we work with very different material, very different oxides, but right now we are working with this very interesting material composed of sodium niobate microcubes functionalized with cerium nanorods. So we have two very good materials for this reaction, and combined they form these cool structures we can see here in slide 11, where the microcube is the sodium niobate and these tiny little bars are the cerium nanorods adsorbed on top of the surface. And finally, we can see the activity on the next slide, where for those who are not very familiar with this plot, this is an electrochemical experiment. But the important thing is that this shows to us a very, very precise information of how much hydrogen peroxide is being yielded. So we can see here in the spreadsheet. Let's take a look at the two references materials that we have commercially available for this application. So Vulcan is a carbon material that it's the commercial reference for hydrogen peroxide generation. We can see that it yields 2.5 number of electrons and 72% of hydrogen peroxide. And we have platinum, which is also a commercial material, but the other way around. It yields very little hydrogen peroxide, only 6%. We can look now at our materials and we can see that with only 1% of sodium niobate, we have 82% of hydrogen peroxide production. So with only 1% of catalysts made by cheap and readily available oxides, we have a material that already performs better than the commercial references that we have for that. Finally, we ran some computational calculations to show to obtain more information about this, and we can see that these colorful plots here on the figure, they indicate that there is an effective electron transfer between our molecule and our surfaces, and this free energy diagram on the right, it shows that the reaction is thermodynamically favored by both surfaces. Here downhill indicates that it's favorable. So we can see that our materials, they are combined in a synergic way to promote both a thermodynamically facile reaction and an effective electron transfer, and that accounts for its great performance. Finally, I would like to acknowledge all the people involved in this research. I'm here presenting to you, but here on slide 14, we can see that the main investigator is Dr. Vanessa Antonin. She's been carrying out all the experimental analysis that I've presented to you. We have done this in collaboration with other MEM groups, but other are actually credited here from the works that I've shown you before. Can we go to slide 14, please? We have, it's a very big group. Not everyone is here, but the mainly ones that appeared in our papers are shown here. But I would like to highlight that we are a very big team. We also work in collaboration with several international institutions and universities, and you can see some examples here. We work with Barcelona, with Mexico, with Canada, Sao Paulo, and so on and so forth. And finally, on our last slide, I would like to acknowledge who is making this research possible. I would like to thank FAPESP and PK CAPS, which are our governmental agencies, struggling to stand over the last few years, and they provide all the financial resources that we've had so far. Also, of course, with Universidade Federal do ABC, where most of this research has been carried out, and all its facilities, both experimental and computational, where the analysis have been performed. And finally, I would like to thank you all very much for your attention, and I am available to answer any questions you might have. Thank you.
Great, thank you very much, Lana. And so that's a nice segue into the questions. I'm going to turn to the co-moderator now, Suryakanta, and maybe you can tell us what questions there are. And if you're still thinking of your question to put in, if you will tell us who you're directing your question to, that will be very useful.
Yeah, thank you all presenters. There are many good presentations, and I think most of them have finished in time. And we have a very good question, a very interesting question. Is it good to use plastic for the collection of samples needed for studying of emerging pollutants, contaminants? We know that micro that may contaminate if you collect water sample in plastic tubes or plastic bottles. So it is not directed to anybody. Maybe somebody can answer that one.
Hi. Well, actually, it's not optimal because plastic can release some molecules that you are going to measure as emerging contaminants, and also because it's very absorbent material. So the idea would be to use glass bottles for that.
Okay. And beside that, there are no other questions. There are a few comments.
Well, maybe you could share some of the comments.
There are no questions now, right now. And this is my personal query, Cristina. So if maybe within few hours we can test, or maybe within 1 day or 2 days we can test. So is it going to affect the quality of water? Any additives from the plastic bottle?
I don't know how fast they can release the additive, but for sure the sorption is an immediate process. So even if you only take 1 hour to take the sample to the lab, you are going to have some absorption for sure. So with the release of other molecules, I'm not so familiarized, so I cannot say for sure, but I guess it would be also fast, because all preservatives are very, very soluble. So yeah, I think it's a...
Okay, then glass is a
it
better
can be an
material.
issue.
Okay,
Sorry?
okay. So glass can be a better material and that can be used.
Mm.
Okay. So there are no further questions, but I have one comment. So whatever the water we are drinking, maybe for decades we are drinking in plastic bottled water, and we have no idea how much microplastics we have ingested, and it has gone to our blood. So that is a dangerous condition, and even I am seeing that many places now they are using maybe glass bottles or maybe metal glasses to serve water. So that is a additional step they are taking right now. So there are maybe
well, beside the drinking water bottles are one of the major problems introducing plastic in the environment. So beside that they can introduce some additive in the water we take, is also that we are producing enormous amount of plastic of just one use. So
yeah, okay, thank you for the answer. And we have no further questions. Back to Mary.
Okay, well, we do have a couple of minutes. I have a question for Edith. I was curious about the negative removal for, I believe, ibuprofen and maybe some of the others. Is there something in the process that actually generates those chemicals, or how was it that there was actually a negative removal? Edith? Oh, maybe she's not with us anymore. If any of the presenters can give you a minute or two, if there's something you would like to add. There was a couple of people I unfortunately had to cut a bit short. Yeah.
Mary, this question that you just made, in the studies that we use as a base for our data analysis, we usually found some data that says the contaminants may be generated in the treatment process, because they use chemicals and they use chemical process to remove the contaminants. And sometimes they combine with the pollutants they are in the wastewater, and they generate some particles that can be identified as the pollutants that we are looking for in the studies. So we have, it's very common. We see negative efficient removal.
Okay, thank you very much for that. I was aware that some endocrine disruptors become more active because the chain shortens, that through the process it actually can cause some of those disrupting chemicals to become more active, but I wasn't aware that that some of them are actually generated by recombining chemicals in the process. Thank you. Is there anyone else Cristina? I see you're unmuted.
In wastewater treatment plants, you can also find a higher concentration of some contaminants in the effluent than in the influent, but just because in the influent the molecule is conjugated with some other, so you are not measuring all the potential molecules that you think you are measuring, and in the effluent, because the conjugator is broken, you can measure higher concentration of some molecules. So you can have both explanation to that.
Great, thank you. Okay, yes.
Welcome.
Yeah, there is another interesting question. Now the COVID-19 pandemic happened in the world. So why the COVID-19 pharmaceuticals still did not considered in the last papers for their removal from wastewater? So maybe I can answer that one. Because many drugs for COVID are pretty new, and we're not using very old drugs. So the new drugs and mostly the supportive care we are using. So these chemicals are very new, and their detection has not yet started. So unless they become old, maybe a few years back, whatever we are saying, like paracetamol, diclofenac, these are very old molecules. their detection method in the water has been there. There is system, and the removal ways are also there. But COVID-19 drugs are very new. Their detection and removal process are not yet very clear, and there is not many studies on that one. So possibly because of that reason, they are not yet mentioned in the papers which are presented here, and this need more study and research.
Yeah, it's very early in the research cycle. These things take time. People have to apply for research grants and go through a process. Plus, the research has to be conducted. So I expect we will start to see some of those research results in, sort of 1 to 4 years rather than immediately, just while the pandemic is winding down. So just to bring our session to a close, then I would like to remind you that if you do have a question that's just coming up right now, feel free to type it in, and we will collect written responses from the presenters for any remaining questions now that we're out of time that we haven't been able to answer. And we'll put the answers on the conference website. Also, the key findings will be published in 5 I-WRA UNESCO policy briefs, and also selected contributions will be published in a UNESCO Springer scientific book that will be compiled just immediately after this conference and then published later. So we'd like to remind you all that you can see really excellent selection of conference posters online at the I-WRA Online Conference.org website. And these can be found under the posters menu. Also, if you have any questions on the posters, you can send us an email to online.conference@iwra.org, and we'll contact the poster authors to respond to those queries. And the PowerPoint presentations that you've just seen will also be made available very soon on our conference website, along with a video recording of the session. So if this isn't your time zone, you will be able to catch it a bit later. So I want to thank again everyone for your presentations and for the audience questions that we did receive in the comments. And also I want to acknowledge the team behind the scenes from I-WRA and UNESCO. So with that, I will turn it over to, I think, Sungphil.
Thank you very much, Mary and Suryakanta, for this interesting session, and thank you to all the panelists. So with this session, we close off the second day of the online conference, and we invite you all to participate in the third and last day of this conference tomorrow. It's starting at 9 a.m. CET. So thank you.
Thank you, everyone.
Thank you.
Great work with you.